There we go.
Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts.
That's the whole positive feedback portion, right? Depolarize to open them, which causes more depolarization. It goes up and up and up.
At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only, and the membrane potential returns to the resting state of minus 70 millivolts.
Now they're going to show you the graph.
The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
Good. Gives you a visual for those of you who are visual people. The only thing that I don't like about this one was just that they didn't tell you how you got from here to here, right? They just went resting straight to action potential. But we all know that what has to happen in between the resting potential and the action potential. Graded potential, yes, you need a graded potential, a depolarizing graded potential to hit threshold. Now, they probably just said, oh, that's a whole different story, but you guys understand that there has to be something in between there, or else you'll never go from one to the other, unless you electrocute yourself, and then you can skip the graded potential, right? Okay. Everybody good? Okay, go ahead.
So is the graded potential the ligated sodium?
It's when ligand, yeah, it's when between here and here, generally speaking, you're going to have a gated sodium channel, but it can't be voltage, yeah? So we were using ligand to get it started. FYI, it doesn't have to be ligand. It could be photon gated, like the one in your eyeball, but I don't know how the hell to draw that, and neither do you. It could be pressure gated or something, but definitely not voltage gated, right? So I use ligand gated to start it. Is that okay? Okay, go ahead.
And do those occur in the dendrites?
These?
The axons?
They occur anywhere but the axon.
Okay.
Yeah. The graded potentials occur pretty much everywhere else, and the axon is the place where you have the voltage-gated channels. Everybody good with that? Okay, so let's revisit where we left off last time, too. and make sure that you guys actually grasp this. Oh, not endocrine system. We'll do that in a second. So the last little part is the whole all or none thing about action potential. So let's look at this with a graph, okay? If you are a sub-threshold stimulus, then you get no action potential, right? Because how many voltage-gated sodium channels do you have to open to get an action potential? Just one, but then you get one, right? So sub-threshold stimuli are, what kind of potentials are these, by the way? Those are graded. Yeah, those are graded potentials. They just didn't hit threshold. But if you hit threshold, let's revisit the concept that we talked about last time. There's no such thing as a strong or a weak action potential. Because if you open the first voltage-gated sodium channel, how many do you open? All of them. So in a cell, every action potential is like every other action potential. And it doesn't matter whether you started it with 10 molecules of ligand or 1,000 molecules of ligand. Because look, this is a threshold stimulus. Maybe this is 100 molecules of ligand and this is 150. A suprathreshold stimulus, they still cause the same action potential. But what we were talking about last time is you don't, in the nervous system, code for intensity with magnitude of action potentials. You code for it with frequency of action potentials. So let's look at that one graphically. You ready? Okay, so these little spikes are just a really simplified way to represent an action potential. Everybody cool? Okay. Subthreshold stimulus, no action potential. Cool, right? Threshold stimulus, action potential, just one. Suprathreshold stimulus, meaning more than, meaning maybe this is 10 molecules of the ligand and this is 100 molecules of the ligand. Then what's going to happen is simply this, that after I cause the first action potential and repolarized out of refractory period, I would have more ligand to bind and cause another action potential, right? And then I'd have more ligand to bind and cause another action potential. That makes sense? Okay, so that's the first suprathreshold stimulus, but this one is dumping a dump truck of the ligand over there. And you're going to have so much that you will only be limited by your refractory period. Yes? This is called frequency coding. And frequency coding is how your nervous system actually tells the body about intensity of stimuli, right? So that was the example that I used last time about poking your finger versus cutting your finger off, right? Okay. So this might be poking your finger with a pin. This might be just barely touching your finger, and this is cutting the damn thing off. But this is per neuron. Yeah? Frequency coding. That's in your notes. Right there. It says frequency coding. Okay? All right, so let's conceptualize, though. Doesn't this depend? Frequency coding depends on how quickly you can get out of a refractory period. Correctly? Right? So if you are still in refractory period, then you can't send another one. So do you see that the whole nervous system really depends on you being very quick to be able to use the neuron again, right? And you could only get another action potential when you were out of what part of the refractory period? Absolute refractory period. You might get another action potential, but it would be more difficult if you were in relative refractory period. Does that make sense? Okay. But here's a concept that a lot of people misunderstand. So listen to this question. Is refractory period related to action potentials or graded potentials? Only action potentials. Graded potentials don't have a refractory period. They don't have to wait for voltage-gated sodium channels to reset, right? Okay? So refractory periods only occur after action potentials, yes? Not after graded potentials. Is that okay? Okay, so this is called frequency coding. Anybody have any more questions about frequency coding? Go ahead.
So on the quiz, my battery's about to die, so I don't know the exact question.
The one about absolute and relative refractory period have to do with, what do they have to do with?
So
It's only action potentials.
no, it's not that one.
Okay.
It's the one that says it has to do. Some of the action or the question
I'm with you.
has to do with suprathreshold or threshold. Because the question itself is to generate another action potential. You only have to hit the threshold.
Only hit threshold, yes.
Okay, so then it would
super
be
threshold will do it, but it doesn't do it any better.
okay.
Threshold or super threshold.
Okay,
Yes.
so that question doesn't have an either or. So then the best answer would be that
Just
you
hit
have
threshold.
to hit threshold.
Just have to hit threshold. You don't need a super threshold stimulus, yes?
Yep.
You just need a threshold stimulus. Yes, a super threshold stimulus to get an action potential. Only thing it would do is get you more frequent action potentials. Yes? That's really the only difference, right? There's nothing special about going above threshold except that it's probably going to get you another one right behind the first one. But if you're asking about a single action potential, threshold. That's all you need. Go ahead.
I think it's the question during the relative refractory period, the second action potential is, so that it would just be threshold.
No. Well, you're gonna have to really, really overdo it if you're in relative refractory period, aren't you? Yeah, you're gonna have to overdo it.
But if a second action potential, if you just need to hit threshold.
Right, so let's see. What's the question? During the relative refractory period, a second action potential can be elicited, not by a subthreshold, but still can be elicited by a threshold stimulus, right?
So
It may take more to get to threshold, but it's still threshold.
Okay,
Yeah.
so it doesn't matter, so it wouldn't be
Still threshold. The threshold doesn't change though. It's just going to be a longer, more chemical it would take to get to threshold. Does that make sense? It would take more chemical to get there.
super threshold is for hyperpolarization.
Well,
What did you just say? I'm sorry.
so a super threshold stimulus just goes past threshold after you get there. Okay, but threshold will get you an action potential, period.
More action potential.
It would get you more frequent action potential, so
During
super
the
threshold.
relative.
During any period, a super threshold stimulus just gets you more frequent action potentials.
But not during the absolute refractory period, right?
Oh, except for during the absolute refractory period,
But
yes.
during the relative refractory.
During any period. During any period except absolute refractory period. Any period except absolute refractory period. Threshold, you just can't hit threshold because the gates are busy, right? Threshold gets you an action potential. Suprathreshold gets you more frequent action potentials. Yeah? Go ahead.
It's per neuron.
Per neuron, yes.
So it's not multiple neurons firing off.
No, we're going to talk about multiple neurons, but we have to get to synapses before we do that.
Okay.
Good? Okay. Everybody good? Okay. All right. So those are good questions. Okay. So we got frequency coding. Now, any of you nerds like flowcharts, or is it just me? I freaking love myself a good flowchart. So I'm just going to tell you that if you are a flowchart person, this fantastic flowchart, which is figure 718, goes through all of this and puts it in flowchart form. It tells you when negative feedback is involved and when positive feedback is involved. If you don't like flowcharts, ignore the hell out of it. I don't care. It's the same crap, just organized in a different way. If you do like flowcharts, it's a good way to stress test and check your knowledge, right? Good? Okay, so now, last thing before we get to some clinical conditions, which will really make this make more sense, is we haven't talked about myelin and myelinated axons yet. Even the video that we just looked at was in an unmyelinated axon, how action potentials work in an unmyelinated axon, right? But you guys, of course, know that if you have a really long axon, you're going to have to myelinate it or else it won't work, right? And you learned about myelin insulating and speeding up axons for a really long time. So how does that fit into this story? It's not very hard to fit into this story. First off, if the neurons are right next to one another, then myelin isn't necessary. Like the whole cerebral cortex, the neurons are right next to one another. You don't need to myelinate the axons. They're short, comparatively speaking. But the axon that goes from the lumbar region of my spinal cord, yes, to make my little toe bend, that is a really, really long axon, and it is not going to work at all in the absence of myelin, right? So you have to myelinate those, right? So I want to teach you guys how myelin is related to the story. It's just basically a little tweak. It's actually kind of cool, but it's a little hard to explain, but we'll be all right. We can do it together. Okay, so you guys remember that myelinating axons makes it look kind of like it's got sausage links along the axon with little bare parts in between. So you got your axon hillock, and then you have these that are called nodes or nodes of Ranvier or neurofibril nodes. If it's got the word node in it, that's what it's talking about. Good? Okay. So how is this related? Okay. What the myelin will do is, I don't know if you guys remember what myelin is. It's a really like a whole bunch of coating of another cell sort of wrapping its cell membrane around and around and around the axon. What it ends up doing is insulating the axon. And here's what happens with it. Have you guys like ever been at the beach and seen like a rocky beach, seen a wave go under a rock and then come out the other side, right? Okay, so here's what I want you to imagine. What I'm going to do is I'm going to have my cell body just like I did before right here, okay? Cell body and dendrites, okay? I have my axon hillock right here like I did before. This is unmyelinated, and then I'm going to have myelin wrapping right here until I get to another node right here. So what is going to happen is in a myelinated axon, what you are going to do is at the axon hillock, you are going to have all of your voltage-gated channels start to be congregated right here, okay? Concentrate on sodium right now, okay? Voltage-gated sodium channels. And of course, if I get a big enough graded potential here, I will hit threshold here. Everybody with me? Okay. If I hit threshold here, what happens is I get, of course, a big wave of depolarization, because that's what an action potential is. But what I do is I hold on to it by wrapping the axon with myelin so that no ions can go in or out as long as you go under the myelin. But then I create a huge electrical wave big enough that it will actually open these voltage-gated channels. The next voltage-gated channels that you run into are at a node. And then what those do is make another big action potential, big electrical change, and then hold it in, right? And it goes under, right? And then activates these. And then it goes under and then activates those. What that ends up doing is making it go way faster down a long axon. And if you went with the metaphor of dominoes for an action potential, right? If you flip over the first domino with a regular unmyelinated action potential, then all of them fall over, right? Okay? This is big dominoes, right? They're really tall ones. You have to flip this one over to make sure it hits that one, right? You have to flip this one over to make sure it hits that one. Does that make sense? So what they call an action potential down a myelinated axon is a saltatory conduction. Because in Spanish and Latin, saltar means what? To jump. But I don't think you should call it jumping, because it's actually diving. Isn't it? It's not actually jumping up, it's actually diving below and then holding on to it. But I can never remember what the Spanish for dive is. What is it, dudes? Spill it. Somebody told me in my last class. David told me and then I forgot immediately. Nobody remembers? What? Clavat? Okay, right. So it's clavatory. Come back. So it's diving. Do you see what I mean? So what you do is you create a big electrical change and then you just don't let it dissipate at all, right? And remember, if you make a big enough, if you throw a boulder in the pond, then you'll feel the wave on the other side. So all you have to do is make a big enough wave there that you feel it here. Then if you open these, it's going to make a big enough wave that you feel it there. Does that make sense? Okay. So this is saltatory conduction. Let's bring this back to a clinical situation. Okay. So now I want to talk about what happens with a myelinated axon if you have a disease that causes demyelination, like MS. MS is an autoimmune disease that causes demyelination. Okay, so if I just take out one of the big dominoes and flip over the first one, does the thing work?
No.
It doesn't work at all. And you just take off the myelin, but you don't have voltage-gated channels all lined up like you did with the small dominoes, right? So if you take off the myelin, does this one actually send the action potential? No, it stops. And how does that manifest in someone with multiple sclerosis? Where do they usually have symptoms first? Hands and feet. The longest one, huh? Yeah, they start dropping things. These are the longest axons that depend on myelination the most, right? So you start to have symptoms in the periphery, both sensory and motor symptoms in the periphery first, because you lose myelination. Does that make sense? Okay, so this is called saltatory conduction, and really all it is spacing out your voltage-gated channels at the axon hillock and then the nodes, right? And then just holding on to whatever change you made until it gets to the next node. Does that make sense? Okay, so with saltatory conduction, it does end up being faster, right? Down the same length of axon, if you did myelinated versus unmyelinated, it ends up being faster going down a myelinated axon, right? But still, you don't need myelin everywhere. If it's short enough, then that's fast enough. If it gets long, then you really have to worry about speed. Otherwise, whatever happened here would have a big lag time before it got to my little toe, right? So the longer axon, the more you need myelination. Everybody good?
So,
Okay.
Melanie, real quick, what do you mean by like diving and kind of like going in? That's what
So-
I'm a little confused.
So is anything actually going out of the membrane? So the electrical wave is not going up, right? It's actually going through the intracellular fluid underneath the myelin. So that's why I'm saying it's diving, not jumping.
So it's not going through the axon.
No, you created an electrical change right here, a voltage change right here. And then I just don't let anything move the whole time I'm going under the myelin.
I thought the myelin was supposed to hold an electrical charge.
It is. That's exactly what it's doing. It's not letting it change. I made it over there. I keep it exactly like it was until I get to the unmyelinated portion. So it is basically you made an electrical change and you don't let it do anything as it goes under the myelin, and then it is still big enough to hit minus 55 right here. But it's not going out. Do you see what I mean?
So it's not going through the axon itself, it's going
Through the
myelin,
intracellular fluid.
through the intracellular fluid
Mhm.
underneath the myelin.
Underneath the myelination. Yeah, it's going through the intracellular fluid
And it's just staying there?
until it hits the node, right? And then when it hits the node, it's actually got access to intra and extracellular fluid, and it will activate some more voltage-gated channels, right? And then you're going to have sodium moving in again.
So
But
it's-
nothing can move under the myelinated portion, right? It just has this voltage change that you created, and if you can hold on to it until you get to the next node, then you're going to open the next voltage-gated channels. Go ahead.
So the myelin keeps the sodium and potassium in the right ranges that it can transmit it.
The myelin just basically makes sure that whatever you did there doesn't dissipate before you get here. Yeah? Okay. Now, the other thing is that we're just talking about sodium channels. FYI, wherever there are voltage-gated sodium channels, same story, voltage-gated potassium channels, and also pumps, right? So you repolarize the same way, you just don't have to repolarize everywhere either. You repolarize there, you repolarize here, you repolarize there, right, in the same way. Does that make sense? Got it? Okay. Yeah? No? Yes? Go ahead.
So the myelin basically just kind of like allows the like signals, the electrical signals,
Mhm.
just like skip a bunch of channels and just go.
Well, there aren't any channels there, but yes, if there were channels, it would allow it to skip a whole region under there. Yeah, but there aren't any. That's why it doesn't work if you take off the myelin, right? So there aren't any voltage-gated channels under the myelin in that region. So you have heard before, of course. Now let's go back to what people tell you about myelin. They say myelin insulates and speeds up action potentials. Am I just not now telling you that it insulates? It's an electrical insulator, so no electricity is going in or out at that point, and speeds up action potentials. That's what it's doing, right?
Just like a power cord.
Yeah, it's holding on, so nothing is getting in or out wherever it is covered. But if you peel it off, the wire will shock the hell out of you, right? So the wire will shock the hell out of you at the axon hillock and the nodes, and you can touch it. Don't, right? You can touch it on the portion where it's insulated, which is where the myelin is, right? Because no electrical change is occurring in those areas. Is that okay? Not do you love it, but is it okay? All right. And if you put MS in your head, right, if you think about MS, you can start to give it an application, right, which is demyelinating. Okay? Who has more questions? Because I don't feel like that actually sunk in for some of you guys.
So no sheath, there's nothing there to keep moving it.
Yeah, there aren't any channels under the myelin sheath. And would you want any channels under the myelin sheath? No, you literally are trying to keep crap from moving, right? So you don't want any channels under there, right? That's what you're doing, is you're insulating those particular portions. You and then you.
I feel like you're reading this and I'm not quite visualizing it. I'm very visual. So when you're using the word under, are you saying the space between the myelin sheath and the axon, like that picture?
Yes, right here.
Okay.
Do you see that stuff is moving here and stuff is not moving under there? Like nothing happens once you get in there, and you've got pluses and minuses moving here, right? Nothing moves once you actually are under the myelin sheath. So it is actually physically insulating the axon to keep things from moving in and out, right? And it ends up so that you really don't have to depolarize the whole axon. You have to depolarize this point big enough so that it hits that point. This point big enough so that it opens that point, right? You don't have to do all of them. You just have to do a big enough one so that it actually makes a big enough wave, a big enough electrical change to make sure that the other one opens, right? Okay? So you don't, even if, let's just imagine, it's not true, but let's just imagine that there were actually voltage-gated channels all along here. You don't have to open them all. You just have to open that one so that it opens that one.
Isn't it kind of like a 4x1 relay where a person
Yeah.
grabs it, person runs.
Yeah. Yeah, I like that. Yeah, that's good. That's a good metaphor too. Got it? Okay. All right. Yeah? Okay. Sometimes I feel like, oh, we just lost each other, and I really feel like I need to stop and need to go back. But so you have to let me know, because sometimes I don't know that we lost each other. But let's try this. Let's do this last clinical stuff. And if something comes up while you're doing the clinical stuff, then you can ask more about it. You ready? Okay. So when I put clinical stuff in phys, it is literally to force you to test your physiology to figure out whether you've actually understood it well enough to figure out what would happen if it broke, right? So with the clinical stuff, again, I'm less interested, because this is not pathophysiology, and you memorizing the signs and symptoms of hypokalemia to figuring out how it changes normal physiology, right? So let's look at these. These are all situations in which you change the concentration of an ion, right? And you guys told me before that you understood, at least theoretically, that if you change the concentration of any ion, that it would change something about the minus 70, right? Like if I had too much whatever in the extracellular fluid or too little whatever in the extracellular fluid, you're like, conceptually, I know that'll do something to that number. Now we're going to get to the point that you can figure out what it would do to that number and how it would impact your ability to send action potentials. You with me? Okay, so first thing is you need to understand how to read these. If it says hypokalemia, low potassium in the extracellular fluid, that's the problem. Everything listed after occurs because of that problem, right? So this is the issue, and these are the things that occur because of that problem. So let's talk about why it's called hypokalemia. First off, conceptually, where are you more likely to have ion imbalances, extracellular fluid or intracellular fluid? Yeah, right? That's where it generally occurs, because you ate too much or too little or something, you puked it all up, you did whatever the hell, right? Okay? That's where it's going to occur, okay? Of course, it will cause a problem in the intracellular fluid, but that's what we're looking at because of that, right? So hypokalemia, low, hypo, below, low K, where? Low potassium in the extracellular fluid. That's your issue. And then let's talk about some ways that that could occur, and then we'll talk about what occurs because of it, okay? So ways that that could occur. Obviously, decreased intake, right? But you'd have to be kind of in starvation conditions for that to occur. Like, it's not just like I ain't eaten a banana in a while, I'm going to have hypokalemia. No, that doesn't occur, right? But where you guys are going to run into it even more frequently, because you're going to be in human healthcare, is if you have massive fluid loss, you lose ions with your fluids. Does that make sense to you? Persistent vomiting, diarrhea, diuretics, right? All of that kind of stuff is going to make you lose massive quantities of water, and you lose ions when you lose water, right? And they're actually going to jack you up long before the water loss is, right? So that it could be the potential problem. The other thing is that we're going to learn some hormones that are responsible for regulating potassium. And if your hormone is off, that will actually mess up your potassium. And then kidney failure. Your kidneys also help you regulate your ion composition in your body. If your kidneys go bad, don't expect your ions to be okay? Because they actually take excess out when you have too much, right? And retain excess when you have too little. And if your kidneys go down, your ions are going to go down. So we'll come back to the kidney thing later. Okay, so here's the deal with this. Hypokalemia, right? Low potassium in the extracellular fluid. That means that I've screwed up my concentration gradient for potassium. Can we all agree? What should it be inside to outside? 30 to 1. But now I have excessively low potassium in the extracellular fluid, so maybe it's 30 to 0.1, which is 300 to 1. Yes? Got it? Okay. You don't have to do math if you don't want to. You can think 30 to 0.1 or 300 to 1, but I did not change the intracellular fluid yet. Okay? You with me? Okay. Now just let it sit there for a minute with a 300 to 1 concentration gradient for potassium, and then figure out what potassium is going to do at rest before I even try to have an action potential. What's potassium going to do? It's going to diffuse which direction? Out. Faster than it normally does. Yes, can we all agree? Okay, so sit there for a minute, let potassium diffuse out, and then tell me what my number will probably be when I'm sitting at rest. It's not going to be minus 70, it's going to be what? Let a whole bunch of potassium move out. No, it's not going to be 0. So what is it going to be? Maybe minus 90, right? Because if you sit there and you let a whole bunch of positives, even more than normal, move out at rest, then instead of sitting there at minus 70, you're going to become hyperpolarized, right? Right? Okay. Now, try to start an action potential. when you were hyperpolarized? It's really difficult, right? It's not impossible, but it's almost like you're in relative refractory period all the time. It's harder to get to. It's harder to get to threshold. Yes. It's harder. It's not impossible, but it's harder to get to threshold. Yes? Okay. So it's harder to depolarize to threshold because maybe you're at minus 90 and you have to go to minus 55. It's still minus 55, right? It's harder to get to threshold. And so it's harder to send an action potential. And so which body systems are you going to see this in? Which body systems are going to have symptoms? Nervous, muscular systems, right? Even cardiac muscle. Okay, so let's talk about the impacts on nervous system and muscular system, and then we'll talk about cardiac muscle. If frequency coding is what makes me have the difference between, it's one of the things, between contracting a skeletal muscle weak or strong, I just actually stimulate it more frequently, then muscle weakness occurs when you can't get action potentials frequently. Yes? That makes sense? Because frequency coding is both in and out. That's how you code for intensity. Sluggish reflexes, both mentally and physically. Sluggish reflexes. Fatigue, you're just tired, right? You just can't get crap going, right? But then cardiac muscle doesn't just depend on action potentials, it depends on rhythmic action potentials. So what you should do in cardiac muscle is you should depolarize and then contract the atria, pause, depolarize, and then contract the ventricles, right? But what if when I tried to depolarize, I didn't always hit it? Then I end up with arrhythmic cardiac muscle contraction. Yes? Cardiac arrhythmias. Does that make sense? Does it stop your heart necessarily? No, we hope it doesn't. But what it's going to do is you might go beat, beat, skip a couple beat, right? Or atria contract in a little too long before the ventricles contract, and they become discoordinated from one another. Does that make sense? Because you don't depolarize to threshold every time you intended to depolarize to threshold, because you're sitting there and you are what polarized at rest? Hyperpolarized at rest. Got it? Hyperpolarized at rest? Yeah? Okay? Okay.
So hypokalemia, is that how you say hypokalemia?
Hypokalemia.
Hypokalemia is pretty much being hyperpolarized too much or too long.
You can't say that unless you can describe the entire process. So don't try to make it shorter. Because it doesn't make a damn bit of sense, right? It doesn't. Like if you just like skip all the middle parts. So hypokalemia changes the concentration gradient for potassium, period. Changing the concentration gradient for the potassium such that potassium moves which direction more? Out more at rest. Let it do that for a minute and then you become what polarized? Hyperpolarized, and then you try to start an action potential, but you're hyperpolarized so you don't get it all the time, right? Does that make sense? So don't try to skip steps in fits, because the steps are the fits, right? They just are. That's like how it works. So let's try the next one. You ready to do the next one? The next one's really interesting and also like really culturally relevant right now. Hyperkalemia is too much, too little of what, where? Too much potassium, extracellular fluid. Okay, that's the issue, right? Too much potassium in the extracellular fluid. Everything that is listed after is occurring because of this. So why could you have this? Massively increased intake, but really only if it's coupled with kidney failure. Because I could eat 4 bananas tomorrow and be just fine as long as my kidneys could get rid of the excess potassium, right? But if I have massively increased intake and my kidneys can't take care of it, then I've got an issue. So do you know anybody with kidney problems? Okay, they have to watch their ion compositions. Like sometimes, for instance, people with kidney transplants can't eat avocados and can't eat bananas because of the potassium. They can't clear the extra out of it. So you guys aren't going to have to worry about that most of the time. But the other thing that can cause this is what if I had massive third-degree burns over a large portion of my body? All of that sequestered potassium that used to be sequestered inside my cells, damage all those cell membranes. Where's it go? Into the outside, into the bloodstream, right? And it circulates, right? So interestingly, people with third-degree burns are at really high risk comparatively to all of these problems compared to the rest of us. And we'll talk about the problems that exist in just a second. But then the other thing, and the reason this is really interesting and culturally relevant, is this is how we kill people on purpose. We actually will give them a massive, massive hyperkalemic dose to do death by lethal injection. And I'm from Texas, So we kill more people in Texas by lethal injection than the rest of the country combined. So I will teach you guys how it actually works. I am not part of that. I am not even pro death penalty, especially once you hear the physiology of it. You will form your own opinion. People generally do. But let's understand the science behind it. Let's understand how it works. Okay, so here's what happens. Okay, so I have how much? Too much potassium in the extracellular fluid, right? And so the concentration gradient for potassium is not as steep as it should be. It should be 30 inside to 1 outside, but maybe now it's 3 to 1, right? Okay. That is not going to impact depolarization as much as it's going to impact what? Repolarization, because don't I use potassium primarily for repolarization? Now, I'm not saying it's not going to do anything to the -70, because it will do a little something to the -70, but that's not the nature of the problem. The nature of the problem is that what you are going to do is I'm going to have an action potential and depolarize, yes? Okay. And then I'm going to close my sodium channels and open my potassium channels and try to repolarize. But if the potassium is at a 3 to 1 concentration gradient, is that repolarization going to occur? No, it either won't occur at all or it won't occur quickly enough for you to use that cell, right? So you get stuck, right? And you are stuck there and you can't have another action potential as long as you are completely stuck there with that repolarization. Even if your sodium channels had reset, if you have so much potassium inside, it's going to screw up the electrochemical gradient for repolarization anyway, right? So you get stuck. If you depolarize and you can't repolarize, then I can't ever use that neuron again. So this issue is too much potassium in the extracellular fluid makes it difficult to quickly repolarize. And until I repolarize, that neuron or that cardiac muscle cell is done, right? I can't get another action potential. Go ahead.
So you're stuck in an action potential?
Yes.
And you're stuck in depolarization.
You're stuck at the end of depolarization because you can't accomplish repolarization.
So you
kind of
can't-
stuck at the top.
So you can shut your sodium channels.
Sometimes, but some of the sodium channels shut on the way down.
Okay.
Not all of
So
them
you're
shut at
just-
positive 30,
Just
right?
stuck.
So, and if I could reset some of the dominoes, but not all of them, right, you still can't play, right? Does that make sense?
Mhm.
So you get stuck in one action potential and you can't have another one because of the concentration gradient. So you can't repolarize, right? Right? And if I can't repolarize, then I can't pump them back into position. And if I can't pump them back into this position, even if I had more ligand, it wouldn't do anything, right? If I tried to bring in more sodium and I hadn't pumped the other sodium back out, it wouldn't do anything, right? So I'm really stuck, kind of at the top right there, okay? So what does this do? Well, this, of course, if you can't use them, again, you're going to have severe muscle weakness, right? Muscle weakness, that's going to be a problem. Can lead to paralysis, but long before you'll have to worry about that, it will stop your heart. And it will stop your heart because I depolarize this cardiac muscle cell to cause a contraction. And I'm stuck. Yeah, I'm just stuck. I can't repolarize it, so I can't use it again, right? And it will actually stop your heart because they depend on depolarization, contraction, depolarization, contraction, depolarization, contraction. If you give a massive dose of this, it's up to 67% mortality rate if you don't treat it. Like if you did this accidentally, and people do, and there's an article about it right here about a nurse who inadvertently gave a really high potassium solution. She didn't actually read the bottle and started with the same thing as another medication. She killed somebody on accident, right? In that situation, so it just basically stops the heart. So this causes cardiac arrest. Now, this is important for us to all know about because we are one of the only relatively wealthy countries, westernized countries, you can't say first world anymore, but what people used to call first world countries, that still has the death penalty. It's really, really uncommon in almost any other MDC, more developed country. And so we're ending up running into some problems because of these policies that we have with lethal injections here. And of course, it's not legal in every state, right? It's still legal in Utah too. So the way that lethal injections work here is it's a triple cocktail. It varies a little, but the thing that stops the heart is always a high potassium solution. What it generally is first you give an anti-anxiety medication to the person that you're about to kill because maybe they're stressed. I don't know. So give an anti-anxiety medication. And then you give a combination of this high potassium intravenous solution plus a muscle relaxer. But the muscle relaxer is not for them. Who's it for?
For everybody watching.
It's for everybody watching and the person actually giving the injection, because otherwise your muscles seize up as your heart stops. So the interesting thing about this, I mean, there's a million interesting things about it, and it's certainly worthy of a conversation. Have you heard? I would love this podcast so much.
So good.
So
that episode is just
it's fantastic, yeah. So there is a podcast, an NPR podcast called More Perfect, and it's about the Supreme Court. Sounds really dry. It's totally fascinating. But I'm a super Supreme Court nerd. I've been obsessed with the Supreme Court since I was 12. I used to write down the names of all the justices, and people are like, "What the hell's wrong with you?" I'm like, "I don't care what you're interested in either." I literally do not care about that teen pop star. So this one is about chasing lethal injection drugs around the world because, interestingly, even though we are a country that still does death by lethal injection, we don't make enough of the drugs to actually supply the needs for the prisons to do death by lethal injection. We actually make very little of these drugs. These drugs are used for other purposes as well, by the way, as long as you use small amounts of them. So what we started doing is we started buying them from pharmaceutical sources around the world, right? But we didn't tell them why we were buying them. Like Alabama didn't tell the UK that it wanted X quantity of this drug for lethal injection. It just said, "Do you have X quantity of this drug?" And they said yes, and they sold it to them. Until one intrepid reporter, she's such a boss, decided that she was going to follow the trail to try to figure out where these drugs were coming from, because no one would be upfront with where they were coming from. And so she started following the trail, and for instance, she goes to the UK and she finds out that this one little bitty quack shop is making these drugs and exporting them. But the legislators had no idea that this person was selling these drugs for this purpose. And so she went and let the powers that be know in one country, shut it down. We got it from another country. She chased it there. She just told them that they were doing, and they're like, "No, we do not do death penalty. Hippocratic oath, first do no harm. We are not selling these for these purposes. Shut it down." And so hopscotching all around the world trying to find these lethal injection drugs until 3-4 years ago, I can't remember, in Oklahoma, that botched lethal injection that happened in Oklahoma. So we ran out of the drugs that we normally use and we tried something new. Then you get to the whole nature of cruel and unusual, right? Because the drug took hours to kill the person. And so regardless of what you think about lethal injection, it's a really, really interesting thing to understand the physiology of, and then probably do a little bit of understanding history and the ethics of. And then you can argue with people from a position of confidence, regardless of what you think, right? So my mother-in-law just tells me no, this is justice. And I was like, well, I want to tell you how it works. And she's like, well, this is justice. And I was like, that isn't even a thing that you can explain. So you lost the argument.
There were 2 points in that I found really poignant, and one being the country that's like, why would you kill somebody and make it look like a medical procedure? Shouldn't it just be like you're killing them? Mm-hmm. And then 2 was talking about Utah.
How Utah got around it. You guys know how Utah got around it?
The dummy bullet, the argument against the dummy bullet too.
Yeah. So Utah said, we're seeing this trend that you're having a really hard time getting these drugs. So our solution is to go back to the firing squad. But you don't want anybody to feel responsible for actually doing that, even though obviously we're responsible for actually doing this. So they give a dummy bullet to one of the people.
But nobody knows who has the
Nobody
dummy
knows
bullet,
who
so they
has
often
it.
be like, it wasn't me.
My father-in-law works at the prison.
Yeah.
They set up the guns and everything, and the officers go in. They're already preset. They just put a trigger in.
Yeah, they just pull the trigger. So anyway, it is at the very least an interesting ethical conversation to have with people whose opinions you are interested in, right? And you may not be interested in mine, and I don't care whether you understand my opinion or whether you agree with my opinion, because I'm in Utah. I'm used to it, right? But I do care whether you understand the physiology. Yes? So you do need to understand the physiology. And all of this rabbit hole crap, I never quiz you on it at all or test you on it, but I promise it'll make you more interesting at parties. Go ahead.
So I just have a different clinical question.
Sure,
not really
I'll try.
death penalty. So when we get a patient who has elevated potassium in their blood, we always redraw it. Is that because of the potential that we've lysed the cell and released all of that potassium that was in that blood cell, and so it contaminated the sample?
I don't know the answer to that
Because
question.
we always do a second blood draw to confirm.
Why don't you see if you can ask somebody why, and then I'll try to see if I can find out the fizz, and then we'll put our heads together. Okay? Because I don't actually know that. I could hypothesize what it is, but I'll try to figure it out. You try to figure it out, and we'll see if we can tell everybody. Okay, so you ready for the next one? This one is hypocalcemia. Hypocalcemia is what level of what where? What do you think?
Low
Calcium in the ECF. Now, we haven't talked much about calcium, so you obviously can't intuitively know this one, right? But I can tell you that what calcium does is, this is an oversimplification, calcium is the latch on voltage-gated sodium channels in electrically excited tissues so that they don't open unless you stimulate them to do so. Okay? They can open accidentally in the absence of homeostatic levels of extracellular calcium. It's just like you lost the latch on your door and sometimes it'll open and you didn't mean for it to. Okay? So if a few of those do that every once in a while because they're not all bound to calcium, then let the cells sit there and it will become slightly what polarized at rest. You open some sodium channels when you didn't intend to. Nope. Depolarized. It sits there at rest and it becomes a little bit depolarized, maybe only minus 70 to minus 65, right? Nothing major. But then if you run into a situation in which you had a sub-threshold stimulus like this, you can accidentally hit threshold and cause an action potential and end up with muscle twitches, right? Sending signals when you didn't mean to. Cardiac problems there too you can potentially have. You can have accidental depolarization. And why again? Explain to me why you get accidental depolarization. Because you were slightly depolarized, right, at rest, right? Just because every once in a while a sodium channel opens when it's not supposed to. And then, of course, the calcium binds again because you're not zero calcium. You just aren't keeping all of them closed all the time, right? So a little sodium diffuses in, right? And so you're sitting around at minus 65. And then you maybe have a depolarizing graded potential for another reason. You didn't mean for it to be an action potential. And it becomes an action potential, right? So why could this occur? All of your hypo disorders can occur because of fluid loss, right? All of them. They can all occur together because of fluid loss too, by the way. Also, massive decreased intake, starvation conditions, really. Lack of vitamin D, yeah? All the calcium in the world can be in your diet, but if you don't have adequate vitamin D, you can't absorb it, so that can be a problem. And then there's two hormones that I always teach in anatomy, but some of you guys may not have learned in anatomy. They're the two calcium-regulating hormones called PTH and calcitonin. If either of those are jacked up, it will jack up your calcium. You don't have to worry about how they work right now because we're going to learn them again in the next set of notes. Okay, so again, in all electrically excitable tissues, calcium keeps the latch closed until you mean to open it. So if you sit around with some of your sodium channels open, then you will be slightly depolarized and easier to hit threshold than you meant to be, right? So symptoms, nerves and muscles have spontaneous inappropriate action potentials. That results in potential cramps, potential spasms, exaggerated reflexes, convulsions. In extreme situations, like if it was hormonal, it could get really extreme. You can go into tetanic contraction, complete tetanic contraction. If you have a baby born with hypocalcemia, sometimes they will go into such tetanic contraction that you can like hold them like a rainbow, like they're. They have to be treated really, really quickly, or else that's going to be a permanent problem. So you might experience this low level if you've ever had an eye twitch. I know you have, right? Like you can't see it, but I know it's driving me crazy, right? What's happening here is these were not supposed to be action potentials, but they're starting to become action potentials. Does that make sense? So it's just twitching. Sometimes that is hypocalcemia. Sometimes it has to do with potassium, right? And either of those hormones are far more likely to get screwed up if you are stressed, because stress hormones will screw up your ions, right? So in that situation, you need a banana, a glass of milk, and a nap. That's what you need, right? Like you're like, I haven't had a nap in recent memory, but I've heard they're great. So what kind of symptoms could let you know that this might be on the way to occurring, in addition to the eye twitches, which isn't always calcium, but it can be? Long-term low calcium, which may lead to hypocalcemia. Some symptoms are dry skin, psoriasis, coarse hair, brittle nails. Unfortunately, all of those are also symptoms of living in Utah. So you don't all have hypocalcemia, but your skin was better elsewhere, wasn't it? Yes, so much better, right? Yeah. I was like, I have to invest in some products since I moved here. Otherwise, I'm going to be a hag like instantly. Okay, so last one. Hyponatremia. How much of what where? What do you think? Low sodium, easier. Yeah? Low sodium in the extracellular fluid. How could this occur? Losing too much fluid, of course. That's the major way that it actually does occur. Is that you could have low sodium intake, but is that a real problem in the United States? No, it is not. Excessive sweating, vomiting, diarrhea, diuretics. That's a serious potential for problem. Kidney failure. Again, if your kidneys are not regulating your sodium, you can lose it. There are two hormones that are involved in water and sodium composition, ADH and aldosterone. You don't know them yet. You will, and then we'll put it back together with this as we go through here. Aldosterone is involved in sodium and potassium, so don't get confused that I mentioned that one twice. Poor diet combined with lots and lots of diuretics, like beer. That's Texas in the summer. You're going to eat crap, you're going to drink a hell of a lot of beer, and then you're going to be outside, and it's going to be 7,000 degrees. So what is going to happen? You're going to pee a lot, you're going to sweat a lot, you're not going to feed yourself adequate amounts of ions, right? You're probably going to be out on a boat, too, right? So what happens in that situation, and I will come back to the ecstasy in just a second, this is the most common electrolyte imbalance. This is the one that is most likely to land you in the hospital just because it makes you act like a wacko. Okay, so let's talk about the reasons it makes you act like a wacko. The concentration gradient for sodium will not be as steep as it should be, right? It should be what to what, outside to inside? 15 to 1, maybe it's 5 to 1. And of course, that's going to screw up the number, but it actually has an even quicker impact because of osmosis. Because if sodium is one of my primary solutes in the extracellular fluid, yes, and I lose a whole bunch of sodium, then my cells go from sitting in an isotonic solution to sitting in a what solution? Hypotonic, right? Let them sit there for a second. What will happen? They'll swell, right? Swelling happens all over in your cells, but if your neurons swell, you act like a crazy person. Yes? And you go in and you're kind of stupid. You're not making a damn bit of sense. They think you are drunk as hell, and you might be, but that is not the issue, okay? Your brain cells will swell. You might even be a little aggressive, but it's usually associated also with low blood plasma volume and low blood pressure. So if you're aggressive but you can hardly like swing a punch, you're probably okay. You're just a jerk, right? So they usually think that you're drunk or on drugs, but then they give you an IV and then you're fine, right? They give you an IV with, of course, ions in it, right? And sodium in it and water in it. So it causes really dramatic neurological symptoms, and that's why you get taken to the hospital on that one, because you're pissing people off, right? Somebody's like, you ain't right. You gotta go to the hospital. Go ahead. Oh yeah, low blood pressure can definitely cause you to pass out. So I'm not even talking about being intoxicated. If you were like this without being intoxicated, you would act like a wackadoodle. So I want to talk about this in relation to MDMA, which is ecstasy. Okay, so we'll talk about how MDMA works when we get to the synapse chapter. MDMA, by the way, I know you have your own associations with it, and it does not do what you've been told. It does not cause holes in your brain. It does have some definite risks associated with it. You will actually know what those are. It is also, however, in clinical trials for PTSD, and they are studying it at Johns Hopkins for lots and lots of depression relieving. So it was actually originally a therapy drug that was used in therapy. And then it got really popular as a club drug, and then somebody made it Schedule 1, right? So you couldn't even do research on it for decades. And now it is back in its third round of clinical trials for PTSD, and it's been fantastic for that. You are not going to be able to get it in Utah, let's be honest, right? It might be legal everywhere else, right? But you're gonna have to move if you got some PTSD in a few years. All I'm telling you. And you might have PTSD just because of living in Utah. No, I love Utah, but didn't we vote just a little while ago about something we wanted to legalize, and then they're like, no, I don't think you get to. And I'm like, I am a grown ass woman. I just told you what I wanted, and they're like, no. I'm like, that is not how that works. So, what does it actually do? So, how is it related? So there have been very few people who have died of MDMA use. I am not saying they haven't damaged their brain. We'll talk about that too. But the very few people who have died of MDMA use have died because of hyponatremia. Because what MDMA will do is, in addition to making you just feel fantastic, it also depresses your thirst response, makes it difficult for you to thermoregulate, and you're not hungry at all for up to 8 hours. Now take that to Burning Man in the middle of the desert. Right? Dance your cute little butt off in your tutu for 8 hours and don't drink anything, right? So what happens is you end up hyponatremic, super, super low blood volume and blood pressure, and then you die because of that, and not because of what the MDMA actually does to your brain. So that's how, there's been a handful of people who've died because of MDMA use, and it was related to ion imbalances and not directly to the MDMA. Go ahead.
What about when they take MDMA and they say that they drink too much water?
Oh yeah, you can dehydrate yourself. So not that you would do this, and right, you're not that person, but you know one. You have an experimental friend. If you don't, you should get one, or else you are the experimental friend, right? I totally have one. My best friend will do any damn thing, and then she will tell me all about it. I love it. I'm like, that dude is really hot. I am totally married. Why don't you go have sex with him and come back and tell me about it? And she's like, gotcha. I'm like, all right, I love it. So, and she also does this. And she lets me know how this is. So you need to tell them that they don't just need to replenish their fluids. What do they need to replenish? You need to replenish your electrolytes, because nobody should die of youthful indiscretions. You should get a pass, man. Don't you think? You should get a freaking pass, right? So you need to tell them why they need a Gatorade. You're like, that's a terrible decision. I hope you don't do it. Here's a condom. Here's a Gatorade. I hope I see you tomorrow. Right? And then you're like, let's make better decisions in the future, right? Because you are grown-ups. You can make your own decisions. So that is how MDMA is related to this. Now, later on, when we get to neurotransmitters, I'll teach you what it actually does to your brain. And then eventually you will be able to make your no decisions from a solid scientific basis, right? Solid scientific basis. Go ahead.
So when someone drinks too much water, I know you can die from that too. Is it
It's
because
really
you've
difficult.
depleted all of those electrolytes?
Mhm.
And then,
Yeah, it's two things. When they're little kids, and I told you about the little girl who drank too much water, right? Her parents forced her to. You can make your brain cells swell. That's what happened with her, with way, way too much water. She overwhelmed her kidneys' capacity to do it. But then in addition, what you do when you're drinking too much water is you're also going to cause other ion imbalances, right? But it's really difficult to do that without yakking if you were an adult, isn't it? Right? It's super duper difficult to drink so much water that you could actually damage yourself. But in a child, it's not quite as hard. Good? Okay. All right, so that is the end of the material. Oh, let me tell you this. You are going to have to do one of these for me on your test, but I'm not going to tell you which one.
One of those four.
Yeah. Uh-huh.
do what, write it out? Or
You're going to have to write it out and explain to me the physiology of one of those four.
with symptoms and everything?
I will explain, I will have you explain how blank impacts physiology. You're going to have to use some potentials. You're going to have to use some polarization. You're going to have to use all of that stuff. Okay? Cool? And the others, I might ask you in multiple choice questions, but one of them you will have to explain to me. Go ahead.
What you said at the very beginning of the class about the other question about how, I can't remember what it was, how something affects physiology.
Mm-hmm.
Will you say that, how you would phrase it again on the test?
I can't remember. I've said it a bunch of times. Explain the impact of cellular respiration to human physiology with a specific example. Okay, so you need to get a specific example in there. And I've talked to a few of you guys about that. How many of you guys have had me before in a class? Okay, so ask them about my testing, right? Just ask them. Because I always think that my tests are total. Oh, you've had me before. You didn't raise your hand. She's trying to hide from you. So these four right here have had me. I think that my tests are totally reasonable and not hard, but they are super duper thorough. So I write the test, I read through all the notes again. If there's something that I didn't ask about but we spent 4 pages on, I want to give you the benefit of asking about it because you just did 4 pages on it. Don't you get pissed off when you study a whole bunch of crap and don't ask about any of it? So I write the test, I read the notes, I edit the test, right? So it goes back to the notes. And I'm looking at the notes the whole time. So that's what you will use as your primary source. Good? Okay. And ask them. Ask them what they think. I try to ask a good smattering of every damn thing that's in the notes, right? Obviously, I can't ask you everything, but I can ask you a piece from everything, right? Okay. Jamon's had me. Both of you didn't raise your hands. Jerks. Both of them have had me too. Okay. So now we are going to switch gears, but you are doing this in lab next week, so I want to give you a little intro to the endocrine system because you start this on Tuesday in lab. Okay. So, and I know that you won't really absorb very much of this today because you're like, I got a test, stop talking. So we're not going to do really hard stuff. We're just going to do a little bit of the intro to the endocrine system. And then let me go ahead and tell you a couple of things about the endocrine system too. And I fixed this today. It was broken. So if you go to melaniev.com with the endocrine system, first of all, the notes are hella long, right? There's like 18 or 19 pages of notes. It's because it takes that long to explain the endocrine system. But in addition, there's also a table. There's a Google Sheets version. I can put up the PDF endocrine table if you want it, but I prefer the Google Sheets version. I'll put up the PDF one. And I fixed this. Link was broken, and now it's fixed. So it's there. Eventually, you will have to know all of the hormones that come from an organ, their chemistry, where they come from, where they go to, what they do. Okay? This is all, FYI, in the notes. It's just really hard to pick it out when it's in 19 different pages and make sure you got all of the right stuff. This is one way to organize it. It isn't the only way. If you come up with a better way, do it that way, all right? This just sort of gives you a checklist of what you need to know about each thing. Cool. If you've come up with a better way, then do it that way. So you have to know the whole notes, and then you have to organize all of this stuff. This is not all of it, because this is just the nouns, right? But then we also have the physiology of how these hormones, for instance, feed back. And it sounds impossible, but again, I put the hard stuff at the beginning of a unit instead of at the end so that you have a lot of time to absorb it before we get to our next test. So you'll be okay, I promise, and you'll have a lab over it. So first off, let's start on the basic functions of the endocrine system. So most of you didn't do endocrine system and anatomy, did you? No? It's because it's not really an anatomical system, right? Is the thyroid anatomically super duper connected to the testes? No, the only way that most of your endocrine organs are actually connected to one another physically is via the bloodstream. But then everything's connected via the bloodstream. So do you see what I mean about it not really being an anatomical system? It's really a physiological system. And so I can teach you the anatomy right now. There's the thyroid gland. That's the anatomy. You got the pituitary gland up there too. And you got some testes down there, at least some of you do. So got some extra ovaries. He's got like a replacement set over here, just in case. Replacement. So basically what we are going to have is a set of organs, and what they really have in common is that they all release chemical messengers into the bloodstream called what? Hormones, yeah, that's what they have in common, right? So the endocrine system is one of your body's 2 major control systems. The other is faster, and we've talked about it a decent amount. What's the other body control system? Nervous system, right? So the nervous system is like sending a text, right? And it's really specific, really quick on, really quick off. The endocrine system is like throw in something in the mail, only it's a blast email, or it's a blast mail, right? You stick a whole bunch of flyers in the mail, and it's going to take forever to get there. They are going to go all over the damn place, right? So it's relatively slow, comparatively speaking, but there is an advantage, right? So advantage. There's a reason you would use hormones instead of neurotransmitters. What do hormones do physiologically that's a little different than neurotransmitters? Yeah, it's more broad. Like you can have a really broad effect by using a hormone. And also, it's longer lasting too, right? Okay? You don't need to release it continuously if you dump it into the bloodstream because then it's in there until it gets cleared out of the bloodstream, right? So you can have a broader, longer lasting impact. Is everybody okay with that? Okay. All right. So endocrine organs, which we saw right here, not all of them are glands. And so I don't call them endocrine glands when I'm paying attention. Sometimes I am not paying attention. I call them endocrine organs because the heart releases a hormone, but it is definitely not a gland. Yeah? So most of them are glands, but not all of them. They all have secretory capacity, but it doesn't mean the whole thing is a gland. So endocrine organs, what they are going to do is they're actually going to generally be really, really vascular. And what they do is they dump something into the interstitial fluid in a really vascular tissue so it immediately gets picked up by the bloodstream, right? So they dump it and it gets picked up. So what they are going to do is dump a hormone, gets picked up by the bloodstream, and it's going to travel through the bloodstream until it finds a target cell with a blank receptor, right? And target cell is kind of a circular definition because what is a target cell? It's a cell that has a receptor for the hormone. What's a hormone? It's the thing that binds to the target cell, right? So the target cell isn't, of course, the same for testosterone as it is for insulin, right? So it's specific to whatever that hormone is. So let's talk about how hormones work in general, and then we'll do like one example that you're going to run into next week because it'll make next week a little easier for you. Okay, so here's the general process of how a hormone works. The organ releases the hormone into the interstitial fluid in a really, really vascular tissue, so it immediately gets picked up by the bloodstream, right? Okay. And it circulates in the plasma, not inside the blood cells. So it's circulating in the extracellular fluid and then blood plasma. And so what is the hormone going to do? Let's assume it's going to do the simplest thing first, and then we'll go back and add some potential complexities. Hormone goes straight from point A to point B through the bloodstream without passing go and collecting $200, right? So it heads straight to the target cell in its current form, or we'll come back and get up the ors in just a second. Let's assume it did the simplest thing, and it goes and finds the cell with a matching receptor, which is the target cell, and it binds to the receptor, and then it produces an effect on the target cell, right? Otherwise, you wouldn't have done this. The effects, again, are called this stupid freaking phrase that I hate because it doesn't mean anything to anybody. It's called a signal transduction pathway. So what I'm going to do is, if I am testosterone and she is a skeletal muscle cell, I will bind and activate protein synthesis of actin myosin, right? So it's the series of steps that makes you respond. But if I am insulin, yes, see if you guys can do this one, because it's good to be able to do this one. I am insulin, and I bind to my target cell. It does what to the target cell? What does insulin do to the target cell? It what? It doesn't enter it. Helps what move? Insulin? Glucose. No, it opens up a glucose. How do you get glucose to move inside cells? Carrier. So that glucose can move in by what process? Facilitated diffusion. Exactly, yes. Right? So, so what it does on the target cell is it causes some kinds of cellular activity change, right? And that's called the signal transduction pathway. And that is specific to the cell and the hormone, right? But it's going to do something otherwise you wouldn't have bothered. Everybody good? Okay, so let's go back for just a second and say, okay, but to get an appreciation for how complicated the endocrine system is, and why, for instance, if I had a thyroid disorder, I would go to an endocrinologist and not a GP. To get an appreciation for how complicated the endocrine system is, sometimes it doesn't go from straight from point A to point B and bind to the target cell. Because it gets dumped into the bloodstream, a bunch of things can happen to it on the way, right? Does that make sense? Some hormones are actually made in an inactive form and have to be activated by your metabolism before they get to the target cell. Testosterone is one of those. Testosterone is actually made from the testes in an inactive form and it goes into the bloodstream. If it never gets activated, the male, an adult male, 25 or so, will look not like he has boatloads of testosterone, but like he has very little testosterone. But then he'll go to the endocrinologist, I hope, at some point, and he'll say, I've been exhausted, I'm starting to lose my muscle mass, I have no sex drive and no drive. And he'll go, oh, endocrinologist, that's probably low testosterone. Let's give you some testosterone, but let's check it first. His testosterone is actually through the roof. It's just not being activated. And would you treat that the same way? No, you would not treat it the same way. Does that make sense to you? Okay. So there are other things that can happen. Here's another thing that can happen. Since it goes through the bloodstream, the concentration of the hormone is impacted by your liver and kidney activity. Liver and kidney usually will break down your hormones. If your liver is overzealous and is breaking down the hormone too much, it will look like you don't have enough of it, but do you want to add the hormone back? No, you want to fix what's going on with the liver. Yes? If your liver was under metabolizing, it would look like you had too much of the hormone, right? But you don't want to treat that before you treat the liver, right? Same thing with the kidneys. Some of your hormones are cleared out of the kidneys. Kidney problems, hormone problems. Does that make sense? So you definitely want to know what's going on all the way through. So it's excreted or inactivated by metabolism. And then the last one is that sometimes hormones interact with one another in the bloodstream, so you have to figure out what's going on. So here's an interesting example. Thyroid hormone is a metabolic hormone, helps to support your metabolism. Okay? Growth hormone is a hormone that causes protein synthesis and cell division. Does it make sense to you that your body actually checks your thyroid level before it commits to growth? Thyroid hormone level? Yeah? And so what might look like a growth hormone disorder is actually a thyroid hormone disorder. Does that make sense? Okay. Now, all of those exceptions, everything but B, C, and everything but A, I don't try to trick you with. So why did I tell you about them at all? Because that is why, if you have an endocrine disorder, you probably need to go to someone who is not also setting bones. Because this crap's complicated, right? And if you don't treat it properly, you can end up having to deal not with just with the hormone concentration, but with upregulation or downregulation. Because you didn't treat it quickly or aggressively enough. Does that make sense? Okay, so let's go back to teach you one hormone control mechanism and talk about, okay, so generally speaking, you don't make the same constant amount of hormone all the time. Your hormone concentration varies up and down based on the body's needs, right? And so if you looked at, for instance, testosterone, and you do not have to even write this one down right now. I'm using it as an example. I'll teach it to you in detail later. If you looked at a male, his testosterone would go up and down. Yeah, it actually goes up and down over the course of a day, a male, right? Can we all agree that there is such a thing as too much testosterone? Even dudes, you guys can agree, right? You've met those dudes, right? You're like, that is not okay. I don't know what the hell's going on there, but you need to stop smashing things. Okay, so you need to regulate the amount of testosterone. Generally, how you do this is by a negative feedback inhibition mechanism. So let me teach you how testosterone works with our last couple minutes. So basically what I'm going to have is when a male hits puberty, same thing with a female, the hypothalamus, you don't have to write this down and you won't be able to fast enough anyway, will secrete a hormone that you don't have when you're a kid. It's called GnRH. That's kind of genetically determined when that occurs, and it's a little different for different people because your genetics are a little different. Okay, that turns on. GnRH is gonadotropin-releasing hormone. You will learn that later. GnRH doesn't go to the testes. It goes to the anterior pituitary, which releases another hormone called luteinizing hormone. Luteinizing hormone, you probably don't know that one yet either, but what that one does is goes to the testes. And then the testes start to produce testosterone. Yes? Okay. Now, this is going to feed back. So I have two questions to you, just logic questions. First off, where would you feed it back? I mean, it's going to go do all its testosterone stuff, right? Yeah. Okay. But how do you make sure that you don't have too much testosterone? It's going to feed back. Where do you think? It actually feeds back to the hypothalamus. Negative or positive feedback? Negative. Yeah, negative feedback inhibition to the hypothalamus. And then it's also, just to make sure it's a really, really responsive, going to have negative feedback inhibition on the anterior pituitary. So what you will see happening here is as soon as you have a whole bunch of testosterone, it decreases the secretion of GnRH and LH, right? And then your testosterone level will fall, right? And then you're not going to feed back, and then your testosterone will go back up, right? And then it'll go back down, then it'll go back up, right? This is a negative feedback inhibition mechanism. Does that make sense? And if it's working well over time, which it does in most adult males, then you have enough testosterone to have a sex drive, have muscle mass, right? Have drive, maintain your bone mass, but you are not zitty and angry all the damn time like somebody in a roid rage, right? And we don't want to see that. Nobody likes that. Okay? So what we will see when you guys finish your test is that basically there's 3 ways to do this feedback. Sometimes it's hormones that are telling you when to release hormones and when to stop. Sometimes it's the nervous system. So let me ask you this as you're leaving. What is it that tells your pineal gland when to release melatonin? Circadian rhythms. That's light, right? Induced. What is it that tells you when to release insulin? Yeah, it's a non-hormone substance. So there's basically 3 ways of controlling hormone secretion. Hormones can control hormone secretion. Nervous system can control hormone secretion. And nutrients or ions can control hormone secretion. But they're all pretty much, almost all of them are negative feedback. Good? Last question, I'll leave you guys alone. Is this extrinsic or intrinsic regulation? Extrinsic, because I'm controlling what system? What system is this? Reproductive system? Yes? It's the roid rage system. I'm controlling the reproductive system, not the testicular system. Okay? All right, I will see you guys on Tuesday? Yeah, I always forget which day this class is. Don't forget